So one thing that we can do with our flame tests is we can actually look at the color of the overall flame and use it to identify our metals or our cations, the positive part of a compound. We can do that by comparing it to other known metals. So for instance, copper burns green. If you see a fire that has green, you know that probably going to have some sort of copper salt. The copper metal is what makes the green, whereas the strontium metal makes the pink. One thing that you're going to be doing in your lab later this week is you're going to be looking at what color is produced by the actual flame and what ion produces that color based on some known flames that you're going to be given. The other thing that you're going to be doing is looking at the actual spectrum of these flames. And we're going to practice using the spectroscopes just to see if you can see any of the lines, but I will tell you that seeing the lines is kind of difficult. It's nothing that everybody can do. But that's okay, because you'll also be looking at some pictures and you'll be able to identify unknowns based on the pictures that I give you that everybody should be able to see. If we look at those colors of lines then, the final thing that we can do is really use the wavelength to determine the amount of energy that was released as the electron traveled through those transitions. So let's say that we wind up with a wavelength that's equal to maybe 500 nanometers. It's closer to our purple end than our red end, so maybe this is a blue or a green. What we can do is first convert that over to meters. And we can use our equalities from before to do that. And remember, if you're doing these calculations, you're going to need to say times E negative 9 or 1 times E negative 9. The reason that we need our wavelength in meters is because we want to stick it into this equation for the wavelength. And since the actual speed of light is given to us on the periodic table in meters per second, we need the wavelength in meters in order to cancel out that part. So our frequency is now 3 times 10 to the 8th divided by 5 times 10 to the negative 7th. And you can either say that that is measured in hertz or 1/seconds. Either way is fine. And then once we have our frequency, we can use that second equation in order to calculate our energy. And so what we can tell now is that the particle of light that was released, or the wave of light, depending on how we're looking at the wave-particle duality, is equal to 3.98 times 10 to the negative 19th joules of energy as it falls back down to its ground state. Big energy would be smaller wavelength. If you have a bigger wavelength, you're going to wind up with a smaller amount of energy. Most things, though, that are within the visible region are going to wind up with -7 as the exponent for the meters, +14 as the exponent for the hertz, and -19th as the exponent for the joules. All of these calculations actually allow us to describe the electron transitions just a little bit better, and these are the type of calculations that you're going to be expected to be able to set up in a spreadsheet. One very last thing, just so that we have it again when we're looking at wave-particle duality for our next step, The fact that the energy has to be absorbed and released within these certain amounts goes into the particle point. There we go, wave-particle duality. These particles of light are known as photons. And that's a word we're going to come back to later, so make sure you have that one down. Photons are just a particle of light. Any particle of energy could also be considered a quantum. You might have heard quantum theory or quanta if it's plural. This is the generic term for a particle of energy. This is the specific term if that energy happens to be light energy. But both of these we're going to be using when we describe Bohr and also Schrodinger's model later. So it's important definitions to have. If you have any questions on any of the things that we discussed in today's lesson, please email and let me know.